Okay, so previously this semester we started by treating particles as if they were all just point particles, little points with a single position. More recently, we started dealing with the possibility that we might have a system of many different extended objects, or an extended object like this. So systems of many objects and extended objects. And we dealt with finding their center of mass, and then we could still basically describe it as a point particle, and we would just use the center of mass as the point we discussed. So in this chapter, we're going to discuss the actual rotation of an object as it spins around. We're still not going to worry about the size or shape change, or we'll worry about the size and shape, but we're not going to worry about the possibility that it can change its size or shape. Now, just like we set up in chapters 1 and 2 some formalism for understanding position, displacement, velocity, and acceleration, we need to set up some similar formalism here. So I'm going to start with just a position vector. Okay, so here's my position vector, arbitrary position vector. And I'm going to imagine that this represents an object moving in circular motion, where the center here is the point that doesn't move. Okay, then if I group these two together, I could imagine this whole thing moving in circles like this. Now I could describe this object in uniform circular motion in terms of the velocity, or at least the speed, at which the edge moves here. But that doesn't work really well in this situation. Let me show you why. Suppose this is not just a circle that one object moves around, but instead this circle represents some kind of an extended object. Well then, I could draw these arrows in any number of positions, and as the whole thing spins around, each point has a very different speed. I want something that's the same for everything on here. You'll notice that this point right here at the center does not seem to be moving at all. We call that point the axis, the point that doesn't move as an object spins around. If this were a three-dimensional object, that axis would extend outward along the third dimension into the rest of space. So it'll be a line that doesn't move as the object spins around that line. But I don't want that axis here right now. Alright, so we need another way of keeping track of how much this thing has spun. And the idea is angles. But to do that, we need a reference point, a reference line. So I'm going to take this and move it out of the way for a minute. And I'm going to make another line, a nice blue reference line, like that. Okay, and we'll bring this back here. And we see nope, that's not what I wanted. There we go. As I move around, what changes is the angle here between the reference line and the object I'm working with. I can turn further, I get a bigger angle. Each of these other ones makes a different angle towards this reference line, but as I turn it, they make the same change in angle with each subsequent turn. So for example, let me start, let's make another reference line. Okay, so now I have two reference lines. And I've got one arrow on one side, the other arrow on the other. But as I turn this, let's get rid of these. You can see that this angle and this angle are exactly the same. So every single point on this disk is going to have the exact same angle of rotation as it turns from a given starting point to a new place. That is what we call the angular displacement from a certain starting position to where the object is at that point in time. Okay, so this angle, if I've got an arbitrary reference position, is theta, and then if I take this and turn it more, oops, there's my old theta, and let's bring this a little bit further so it's not behind the other reference point. Here's my new theta, theta final, and the difference between them is simply delta theta. I made a mistake. Theta final goes all the way to here. Okay, so that's a change in angle. And that works even if this object is not a nice circle like this. Suppose I make that object let's get rid of the angles. I can make this object a ugly squiggly mess. So here's my ugly squiggly mess, but I can still have the object turn in circles relative to the reference point, and I've messed up my axis, but that's the idea. Alright. Okay, just to talk a little bit more. So the angle is between my line of interest and a reference point. How fast that angle is changing is the angular velocity, and how quickly that angular velocity is changing is our angular acceleration.